So, in the last video, we started by asking the question, when is f of g of x equal to g of f of x? And we got a little sidetracked looking at one-to-one functions. The reason that we did that is because f of g of x is equal to g of f of x when they are inverses of each other. And in order for a function to have an inverse, it needs to be one-to-one. So this is the culmination of all of the things that we've been doing in this module. Now, in Module 8, we looked at two inverse functions. We looked at the function e to the x, and we looked at the function log of x. So that was our first look at the most famous pair of inverse functions. So there are two ways to find the inverse of a one-to-one function. You can see here I have this dashed line, this line y equals x. So if we flip our one function over that line, it would make the inverse of that function. So we can see if we flip the blue one over the dotted red line, we would get the green function log of x. Now, we also had a different way that we talked about this. We did this conversion where we said y equals e to the x, and we can convert that and say that's x equals log base e of y. Or if we were just using some regular numbers and not e, we had this as, I think, b, as base. Well, what do you notice about this log and how we would normally write it? It's just that the x's and the y's are flipped. And that is what it means to flip it across the line y equals x. It means to switch the x's for the y's and the y's for the x's. So we can see, why is it that we have the inverse function for these one-to-one functions? Because every x goes to exactly one y, and every y goes to exactly one x. So we can just reverse. Now, if we don't have the picture, and let's say we want to do this algebraically, we'd have to do it like we were talking about down here. We can write this as y equals x plus 3. To find the inverse, we will switch x and y, and then we'll solve. So this is our new inverse function. And we'll normally write this as f to the negative 1 of x. Okay. So let's look at another example. Square root of x minus 5. All right, so we'll look at another example. We'll write it as y equals the square root of x minus 5. We will flip the x's and the y's. And now we need to solve for y. So I can square both sides. And I can add 5. And that would give me this g to the negative 1 of x is x squared plus 5. And you may be wondering, well, wait a minute. X squared plus 5 is not 1 to 1. The x squared was the only thing that failed last time. So let's try to see what's going on here. Square root of x minus 5 is the square root of x function shifted to the right 5. X squared plus 5 is x squared, but shifted up 5. And if I draw this dashed line, it's y equals x, you can see that something weird's going on. This only has one curve, and this seems to have two. And what that means is if we're talking about the inverse, we have to be careful. These functions look like inverses of each other. So how can I make this x squared plus 5 look like this one piece? And it's all about that domain. So you can see here my domain in this case should be from 0 to infinity. And that's our real answer. So why domain 0 to infinity? Well, what's the range of this function? It's 0 to infinity. So when we take the inverse, when we switch the y's for x's, that's what determines the domain of the inverse. All right, one more example. Now what about the cube root of x minus 1? So we'll rewrite it. We will switch our x and y. We'll cube both sides, and then add 1. Now, let's stop and think. Last time we had this issue. Last time, we had to restrict our domain. Do we have to this time? And the answer is no. Because the cube root of x minus 1 its range is negative infinity to infinity. So do we have any restriction here? No. So the only time we have to worry while we're doing these inverses is when we're looking at things like the square root of. Since it has this restricted domain, we have to be very careful. And that's everything we need to know about finding the inverse of a one-to-one function.